Okay, so we found some, at the cost of a lot of time, we found some nice property of Newtonian mechanics. Invariant under these transformations of Galilean relativity as observed by one observer and as observed by another observer moving relative to the first with a constant velocity, physics is the same. What makes that a principle is what you do when it doesn't work. And when it doesn't work is when we introduce Maxwell's equations. Electrodynamics causes a problem. Remember, Maxwell wrote down his equations as a description of the interactions of electric currents and electric charges and magnetic fields and so on. And he found, when he wrote the right equations, that his equations admitted wave solutions, and he computed from known measured quantities the speed of those waves and discovered that it agreed with the measured speed of light, and therefore had discovered that light was an electromagnetic phenomenon. But he measured the speed of light. And what that means is, now that you remember our velocity addition formula, was that the speed of light as measured by the black observer or the speed of light as measured by the blue observer, they should get different results depending upon which way they're moving. If they both time the motion of a pulse of light, they should obtain different results. So Maxwell's equations can at most hold for one of those observers, and the other observer must detect different electric and magnetic phenomena so that when they compute the speed of light, they will get an answer consistent with their measurement. A technical way of saying this is that electromagnetism, the equations, Maxwell's equations, are not invariant, do not retain their form when you do the change of variables that we called Galilean relativity transformations, what we computed in the previous clip. So there are two possible solutions to this. I mean, look, Newton, albeit with some error, computed the speed of sound already, and sound moves with a speed that you can compute, and it moves with that speed through air, and if you are moving through the air, or if there's a brisk wind blowing, then of course sound will move at two different speeds, upwind and downwind, because it moves at a constant speed through the air, and then, in addition, is carried on by the air's motion. So the solution that Maxwell, in fact, suggested is that there is something called, he called the luminiferous ether, some medium through which light propagates. And it's the properties of this ether that cause light to propagate at speed c, much as it is the properties of air that cause sound to propagate at the speed at which it propagates. And Maxwell's equations would then be valid for observers at rest relative to this ether. Just like the speed of sound would be measured correctly for an observer. If there's a brisk wind blowing, you would measure different properties of air compared to what you would measure in steady, stationary air. And when you are moving relative to the ether, the velocity addition formula will tell you will measure a different speed of propagation of light. The other, much more radical solution, which will turn out to be experimentally verifiably correct, in fact, is that light propagates with a uniform speed c through space. There is no real ether, no material implementation of the medium through which light propagates. The medium, if you want, is space. Maxwell's equations, in fact, hold for all inertial observers, whatever their constant velocity. Remember, an inertial observer is one for whom Newton's first law holds. That means that all inertial observers relative to each other are moving at constant velocities. We don't know who the rest observer is, but we know what the collection of all inertial observers are, all those for whom Newton's first law works. If Newton's first law works in your measurements, then when you measure the properties of electricity and magnetism, you will find that they obey Maxwell's equations, and therefore if you measure the motion of a pulse of light, you will find that it moves at the speed c, and the speed c will not depend on your velocity relative to another observer. This contradicts common sense, so let's see why it is that we believe it. Indeed, the initial idea was that Maxwell was right. There is an ether through which light propagates at speed c, and then your task is to measure your velocity relative to the ether, and you can do that by measuring the properties of light. And you do this with the following experimental apparatus. In Einsteinian terms, it's called a light clock, in others, an interferometer. What you're doing is you will set up two mirrors separated by a distance L, as drawn over here on the right, and you will set up a beam of light to bounce between them. We know how to do this. This is a technology that was well developed in the 19th century. And you can imagine that over here on the mirror on the right, there is a counter that ticks over. We have a pulse of light bouncing back and forth. Every time the pulse of light hits the mirror on the right, a counter ticks over. You now have a clock, and it's a good clock because the speed of light being a constant, the time that it takes light to bounce back and forth through this interferometer is twice the length divided by c, because that is how far light has to travel. So this is true if light moves at a speed c. In other words, if you're at rest with respect to the ether. What happens if you take this whole clock and, assuming that the transparency is at rest with respect to the ether, you set this whole clock moving at a speed v to the right? Well, what that means is that when the light beam starts out here and is moving to the left, the mirror on the left is itself moving to the right towards the light beam. The relative velocity between the pulse with which the pulse of light is approaching the mirror is, of course, c plus v when moving in this direction. Let me use red pen to indicate the motion of light. Relative to this moving interferometer, the speed of light in this direction will be c plus v. This is exactly the velocity addition formula we computed. On the other hand, when light is moving from the left mirror back towards the right mirror, then the right mirror is receding from it, and the light pulse will be closing on the mirror at a speed c minus v, and so it'll take a shorter time for light to move from here to there than it does for light to move from here to there, but you can add the two, and you can obtain the time that it will take light to move to the left and then back to the right by taking the time it takes to move to the right plus the time it took to move to the left, and doing some algebra, you can write it this way. You see that the faster the clock is moving at the end of the day, the longer it will take for a light pulse to move back and forth. If you think about it, that's because it spends more time moving at the slower velocity, because this is a larger number with a smaller denominator. Okay, so moving the clock should slow it down so you can measure. Yeah, but how do you know what the speed of the clock is when it's at rest if you don't know what at rest is? Remember, it's hard to detect when you're at rest. Well, the trick is, that was what the clock will measure when it's moving along its axis. What happens if it moves perpendicular to its axis? So now we're taking the same light clock, except now the motion is with a speed v in the up direction. So we have those two mirrors and they're moving up. Of course, now if a light pulse bounces off the right mirror and moves directly to the left, it'll just go off into space because the left-hand mirror will have moved up in the time that it took the light to traverse the clock. And so the light beam that we're interested in is a light beam that bounces back and forth between the moving mirrors. So it bounced off the red mirror here, hit the mirror on the left here, will bounce off and hit the right mirror back there when the right mirror has moved up to this position, right? So, and what we want to know is how long it takes light to traverse the clock when the clock is moving in this direction. This is a geometric calculation. We're going to assume that despite the fact that there is a small motion relative to the ether of the light beam, that this angle is small enough, or v is small compared to c, and to leading order we are going to assume that light actually moves with a speed c. What that tells us is that if little t is the time it takes the light pulse to go from here to here, and by symmetry, little t is also the time it takes it to get back. So big T is going to be just little t here is half the period of this light clock. Well, we can do a calculation over the time little t the light beam has traversed a distance c times little t. In the same time, the clock has moved up by a distance v times little t. So that's this vertical blue segment over here. The distance between the mirrors is L. An application of the Pythagorean theorem shows us that L squared plus v squared t squared is the square of the length of the hypotenuse. We can solve this for t, and we find that t is given by this. Remember that the period of the clock is twice t, so we write it down, and we see that moving transversely also slows down the clock, but by a different factor. Notice the square root here. So the light clock slows down by one factor when it's moving longitudinally, by another factor when it's moving transversely. If we spin the light clock around and assume that the Earth is not at rest with respect to the ether, we should find that we measure a periodic change in the period of a light clock as its relative motion with respect to the ether changes in its direction. And this measurement was essentially done to a very high precision by Michelson and Morley in 1887, and their result is that there is no change. There is no periodic change in the period of a light clock. And so there are various theories advanced how to understand this. Perhaps just as if you measure the speed of sound on average, north, south, and east, west, you get the same answer despite the fact that the Earth is rotating to the east. Perhaps the ether is being dragged along by the Earth. Lots of complicated ideas. the simplifying Gordian knot resolving solution of Einstein proposed in 1905 is there is no such thing as the ether. Maxwell's equations hold in any inertial frame. The consequence is that you have to change your rules for velocity addition. Galilean relativity needs modification. Deep changes in what we think of as the obvious properties of space and time are necessary. But remember, Newtonian physics needs to still be valid, and hence Galilean relativity, in some appropriate limit. So we're going to take Einstein's idea and see what it tells us, and then show why we believe it.